This presentation is delivered by the Stanford Center for Professional Development.
Good afternoon and welcome to our final lecture in this quarter of Engineering and Climate Change. I have really enjoyed this. I thank you for being such good students. Now that we're here, I hope we've provided you with a start on what you need to know to go out and make your own impact in the world with some really real and well-considered contributions to the challenges brought by climate change. I think this will be the issue of your careers if you choose to take this on. And keep in touch. You've got my email. I'll put it up again right at the end of class too. I would love to hear about if you have climate-related adventures to share. I would love to hear them. As you know, we've covered a lot of ground, and today we're focusing on ice as one of our big deals. I want to get my mouse here so I can point to things. Yes, so here we are. We've seen the tip of the iceberg. We will continue from there. And we've had a phenomenal array of lectures. I am struck every time I teach this, the generosity with which people with astounding backgrounds and astoundingly busy schedules come here so they can share what they know with all of us. That's a very generous thing on their part, and I'm amazed time after time. So today we're going to talk about, of course, wrap up engineering climate, deliberately engineering climate, my own research project in that area, and just any wrap up you've got that we need to do. So here's how to reach me, my Stanford address here. The class lecture summaries are giving me the attendance. They're what I grade you on for this pass, no pass. We'll get into more of that in a second. And the videos will stay up through SCPD for the end of the quarter, however they define that. So the end of this week, certainly, probably the end of next week. And beyond that, I think they're going on YouTube. So if you need to catch up on anything, I would try to do it by the end of this week. And thanks to those who did meet over lunch sometimes for the office hour before class. That was fun. An occasional thing, a nice treat when it happened. So for your homework for today, please submit the summary for this lecture and any missing lecture summaries by Monday, so I can go ahead and submit grades. I assume you want them soon, just so you wrap up and make sure you passed and all that. If you still have more than one missing summary by Friday night, I'll send you an email over the weekend to remind you. And my requirement is you just need to turn in 9 out of the 10 summaries. So if you're missing one, especially if you missed the Will Chua one, which then got taken off the site, I'm certainly not going to give you a problem about that. And if you're missing some of the questions for the lecturers, stress not. The idea of that really was to get much better interaction going with the lecturers. And if you got them in, and a lot of you did, really thoughtful questions, that really helped inspire the lecturers. So I appreciate it. And I appreciate the ones that I've gotten to see too. As of about 9:30 this morning, I could see all the ones that you'd sent, and it let me know some of what you wanted to cover. So thank you for that. But if you're missing them, don't worry, you will not flunk the course from that. But those who did, you made it better for all of us. It was great. Readings for next week, of course, none. So good luck with finals. This is one class where you get to wrap it up pretty quick. Yay. If you would like to have, it strikes me you might like to have a class alumni email list going so that you can keep on doing climate-related discussions with each other or with me. Let me know, and I'll put those who want to do that in touch with each other, feed you each other's email addresses. But if this is not of interest, don't worry. There's no requirement at all, and I won't automatically put you on a list. This goes for our auditors, too. If you guys want to be in on a discussion, just send me an email that you'd like to do that. And then the same information opportunities that we've been showing before at Stanford and nearby. We got a new one from Hazy. I think this is a little different way of looking at the energy seminars here through the featured video, so that's nice. This AGU meeting is going on this week up in San Francisco. I have heard that there are nearly 30,000 earth scientists, et cetera, up there in attendance. I went to the icebreaker reception on Sunday night, and I was like, oh my word. So there's a lot of people up there, and a lot of them are obsessing about ice, which you'll hear about today. There's student rates. If any of you can get away, I think the student rate for a one-day pass is pretty minimal. And it's up in the Moscone Center. So that's one way to get up to speed on a lot. And then there have been a lot. I'll put this on the site too, so you don't have to frantically be writing this down. But a lot of you have sent some really great suggestions lately on some interesting things to be looking at. So we'll go ahead and have those on there, a bunch. And there are some proposed lectures for next time. Appreciate that. We always want to grow our roster of terrific lecturers to have in here. You're welcome to take the class again for credit. I believe it's permitted, but there will probably be some lecturers the same, and the plan is to teach it every fall. I got to see, as part of the kickoff for the AGU meeting, this phenomenal documentary, Chasing Ice. It is remarkable. It's remarkably beautiful. It's remarkably disturbing. This cinematographer, who used to be a scientist and consorts with a lot of really experts in ice, has roamed around the planet placing cameras with timed photos and has collected years worth of data now on many retreating and collapsing glaciers. And it is beautiful. They do it as a human interest story as well. It's remarkable. And it's only in theaters for a short while. So take a look at that and follow up if you're interested in that. I would say if you're concerned about climate, you've really got to see this film. This is from Ken Caldera, who gave the geoengineering lecture the first time I taught this class, and you'll see some of his slides interspersed. There's online discussion groups specifically about geoengineering if you find that of interest. And here's a few photos from the Chasing Ice trailer. A truly remarkable film. I think the closest one right now is at the Embarcadero up in San Francisco, but you can sign pledges online that you will go see it, things like that, to help it stay in theaters for a little longer. So this week's guest lecturer, it is I, and no surprise there. And I thought I saw faces last week when I started to go over my background that looked interested, and some of the questions sounded interested. So basically, I am a person who's done a couple fields of engineering and been very happily at work trying to increase the efficiency with which we were using our oil resources, and then going ahead and using MEMS, microelectromechanical systems, for all kinds of things, consumer products, health. These days, a lot into the healthcare area in my consulting practice. My consulting practice, by the way, was founded, we started out with mostly women, which is quite a change from those old days when I was at MIT. I was there in the era of 10% women undergrad. And to be able to have in my consulting company of about 16 of us working together have mostly women. Yeah, think how weird the dynamics are, at least as weird as you think, when it's just 10% women of the undergrads on campus, and then the graduate population was far less. Strange times. Things have certainly gotten a lot more balanced since. But now in my consulting company, we are over half women. And in the management positions, very much women. So it's a different world. So an engineer, deep engineer by background, who has become obsessed with climate. That is what I call my inconvenient hobby for the last 6.5 years or so. So what happened? You'll get to hear a little bit of that. But I decided that was the key question of our age, especially fueled by having kids, which is what also fueled my getting into consulting. You know, how do you make room for that, and how do you plan for their future and add to your to-do list of all the things you worry about, you know, getting them through college, all of that, to add habitable planet matters. So that's sort of the short story of how on earth did I get into this. So let's start talking about some of these slides you'll see from the first lecture that we gave, the introduction to this, where I spoke about what is the climate problem, and then we had that wonderful excerpt from Terry Root, who sends her greetings but just could not come this quarter. But if you ever want to talk to her or send her questions or something, I'm sure she would talk to you. She's phenomenal. So this was the Earth's energy balance. Beautiful slide, just detailing there's a lot of energy coming in. Some gets reflected here, there. There's this whole water cycle going on with its own energetics. There's energy absorbed by the atmosphere. And then there's this whole interaction that's happening with the greenhouse gases and the re-radiation. And that's, in a very beautiful nutshell, what Earth's energy balance looks like. Another way to think about it is that as we're changing our atmosphere, as we're running this unprecedented experiment on what our atmospheric gas composition is, we're changing the set point. We're changing that equilibrium value here, and we've changed it, moved the set point up. And so this, I showed this also the first time. We'll go over the old stuff pretty quick. We have actually got our CO2 concentration from what it's been over the last 400,000 years. You can see up here, we've spiked it now. We've spiked it in a way that we haven't seen before. And people get this kind of data from ice cores, things like that. And so it's good data. And we're in an unprecedented spot. So what on earth do we do about it? You've seen also that the experts are saying, here's another Ken Caldera slide, that the temperatures are continuing to increase throughout this century in every plausible emission scenario we see. No practical way to reduce temperatures in this century is what they say. So what do we do? Here's the motivation for looking into geoengineering solutions, and frankly, looking into them before our backs are to the wall. Because the last thing you want to do is to end up in a situation where you say, our temperature is rising, we're seeing our species becoming extinct faster and faster rate, let's do something now, and not have studied it and not have considered the consequences. So people like Ken are looking, people like me, are looking at solutions, we hope, in advance of when they might be needed so that people don't get tempted to take rash and sudden action. And here we are again, all of these scenarios that people have made. We tend to exceed the worst, the most pessimistic scenario that has been made. So these are, right, here we are, putting in the 2005, 2006 numbers, it just keeps getting worse. And so preventing any further warming requires near zero emissions, but in fact, you know, the CO2 level that's already in the atmosphere is predicted that it will raise our temperature, global Earth average, by a couple degrees C now. So this is pretty bad, and what does this mean? What are the probabilities? This was the last time I looked at the MIT Wheel of Misfortune here, and you know, the chances look absolutely excellent that we're at least in for 3 or 4 degrees C increase, and that looks like we might be lucky. And that's just in a few short years that the scenarios change to that, because we keep exceeding the worst scenario people have said. And why do we care? Here's the one that motivates me a lot, is this extinction. The same thing Terry Root was talking about, the mass extinction of species. But as you look at this site, this was put together, this slide, this was put together from the Ipcc, I think the 2007 assessment report. There's really a lot of really quite dreadful things that happen. So what do we do? Well, one thing I do, I've got to say, some of you asked why I got into teaching. You know, anything I can do in the rest of my working career, I think pales in comparison with getting some brilliant students motivated and educated in the right areas so that you folks can educate yourselves the rest of the way and take this on, right? You're much earlier in your careers, and there are many more of you, and this is the hope, because this is a dreadful problem you've been handed, and you know, there are a couple choices. One choice is this, right? Which is just feeling, the Mack truck is coming. This frankly is how I felt after I watched the Inconvenient Truth movie, standing between the Mack truck and the little kid, the innocent kid who doesn't deserve this. And I don't like feeling paralyzed, but positive action I find helps a lot. So what are we concerned about? we're concerned about all the things you hear about on the news, right? Ocean temperatures and sea levels are rising. Now, back in 2007, it was still the deal that the ocean temperatures were what was mainly responsible for the sea levels rising, just thermal expansion. But these last few years, enough ice has melted that wasn't already floating in the ocean, which doesn't do much for sea level, but enough has melted and added to the overall inventory there that the sea levels are rising in large part because of that as well, which is a big deal. And I was just talking to somebody at the AGU conference on Sunday night who was saying Chesapeake Bay, they're up 17 inches already. That's not the worldwide average, but different circulation patterns, Gulf currents and such. Some areas are getting it far more quickly already, 17 inches. The Earth size coverage is shrinking. You've certainly heard that, and it's amazing in the suddenness to which it's accelerated. And this all serves to shift weather patterns. So if you're trying to grow crops, if you're trying to have enough drinking water, if you're trying to live, this will affect you. And of course, critters are taking it in the teeth too, right? Very much. That's that whole extinction scenario. So, not a pretty thing. And we could get stuck there. We really could get stuck at just saying, oh, this is horrible. But frankly, that's no great place to live. So let's see what we can do. And so, again, some of you seemed interested in this. This is why I will tell you one woman's journey. But moving past paralysis, I really thought, what on earth in this whole thing can I grab onto? And I'm hoping this survey course has given you all enough. I mean, a lot of you came in with a lot of expertise already, so you probably already know what you want to grab onto. But if you didn't, just what part of this do you want to grab onto to try to do something about? And to me, it was, well, what about an environmentally benign, removable artificial ice cap to help rebuild ice and snow, help tip the balance back, because ice is a big deal. And you know, I have a certain amount of perspective at my time of career. So my first spreadsheet on the project I called Global Crazy Idea, right? Because what are the chances that, yes, I see the appreciation there. Because what are the chances that a person not trained in this area, you know, one of 6 billion people, not a climate scientist, is going, well, over 6 billion people, is going to come up with an idea that will do any good after all? You know, persistence, and you guys probably all have a lot of persistence and a lot of intelligence to be here, right? Has you, well, can I figure something out? I don't need to give up right away. Let's just keep working on that and getting expert advice. So Steve Schneider and Terry Root, thank goodness, I got to take their summer course. I got to talk with them, and I got some key encouragement of, no, this isn't nuts. Go try it. And then GSEP, right? You've got so many wonderful resources right in your backyard here at Stanford. And then went ahead, why would you file a patent application on this stuff? Because I've been in technology long enough to know that you can't decide not to, and then a year or two later after you've published go, oh, I should have. Patent law will not let you do that. So if you think you might want to protect it and you think you might commercialize someday, go ahead and do it. So it's that reflex. You can't put the genie back in the bottle. So that's kind of how I got in it. It was really that feeling led to, let's start thinking about something concrete and see how far we can get. Frankly, you know, if the main thing that comes out of my particular 6.5 years at this point, working on trying to slow down ice melt, if the main thing is that one of you says, ah, that's nice, so I love her idealism, but I've got a far better idea. Yes, that's a win, right? Because that's a win. So what's important to look at here? If you wanted to, we've got a lot of slides with a lot of words coming here about climate, but what are we really after? Well, the key problems seem to be stop the increase of CO2. At least let's not let it get any worse. And so the ongoing CO2 emissions levels need to be reduced. And so everything we've been learning about electric cars, about liquid fuels, you know, better building, just the whole sequence that we have learned in this class of various things people are worrying about, they're all so important. And we've got to not increase our methane levels, which are worse, a more powerful greenhouse gas than CO2 is as well. So we've got two things we've got to keep our eye on the prize there. And that's conservation, alternative energy sources, all the list that's very familiar to us. Furthermore, if we can, we've got to bring the levels down. If we could do some of the carbon sequestration methods that people look into to bring the levels down that are in the atmosphere, or down in the ocean, where the ocean acidification is killing a lot of the marine life, that would be huge too. So there are very important things, not mutually exclusive. We need a bring everything to the game type of approach. And in the meantime, this is Leslie looking at all of this going, that's great, we need to do it, but it might not be fast enough. That's when you start thinking about geoengineering. So what are the Band-Aids in the meantime? And believe me, probably more than most of you, I'm guessing. The moral repugnance of getting into that, it's like, golly, I think we need it, but I don't even want to know I'm working on it, was my feeling of the first few years on this, because it really is. Talk about hubris, the kind of stuff that got us in here in the first place. Man can do no wrong and there will be no impacts, but sometimes you have to consider unpleasant things. And so let me make this plea. I hope you've looked at or can look at the LCA lecture that's on the site as well, on the material site, the life cycle analysis. You know, any framework you have to try to consider as many implications as possible of what you do are going to be very key, especially, I think, if you're going to start trying to muck with planetary Band-Aids. So here in the more formal sense, you know, here are our choices, right, as we talked about earlier in the quarter. Mitigation, adaptation, and geoengineering. And by mitigation, it's the conservation, energy efficiency, all of that. The adaptation are things like poor old New York City, right, suddenly realizing, whew, we are really going to have to do some vast re-engineering as far as sea level rise and major storms go. Wow. And then the geoengineering. So the motivation here is possible emergency backup if all else fails. But you've got to do the research in advance. You're not going to do it while they're pointing the gun to your head of, we're going up another 2 degrees. And the moral hazard, what has become very clear, is that people who tend to be climate deniers will apparently often take, from that standpoint of, oh, there isn't a problem, the observation is that they will quickly, if they are presented with an attractive sounding geoengineering solution, say, but we can solve it with that if there is. So there's this moral hazard of let's not change our ways, let's not change our energy mix, let's just keep on the path that we were on, and there's a fix already for us. And so there's a real problem with counting on this. One should never, ever think that geoengineering will solve it all and not do all those other necessary things we need to do in the mitigation and the adaptation. So here are, again, courtesy of Ken Caldera, some of the ways that you can look at saying, how do we stabilize the climate? Here's our end goal. Well, diminish the end-use energy demand, produce the energy without carbon emission, remove the greenhouse gases from the atmosphere, or reduce the amount of solar radiation absorbed. And a lot of people are looking on this end of things in various ways of reducing, they call it solar radiation management, SRM, and that's a focus for a lot. And so here's another way from this book. This was from the Royal Society Geoengineering Report, but there's also Engineering Response to Global Climate Change, this book by Robert G. Watts. Very good summary. And in fact, if anybody as a parting shot wants to borrow this because they don't have a lot of finals and make an arrangement to get it back to me sometime, this is a good one. Okay, I don't see a lot. You guys all have classes. That's a good one. And so here are 2 ways of looking at it. Again, I think we have to bring everything to the game. But carbon dioxide removal techniques, vastly important. And solar radiation management techniques. A lot of people looking at that. And so there are different categories of this. You can make a deep study of this. We don't have time to make a deep study of this, but just know that it's there so that you have enough information you can dig in deeper. And a lot of what GCEP does is looking at these carbon dioxide removal techniques. So there's a lot of expertise in-house here. Basically, what are we going to do with it? Are we going to collect it? Are we going to put it into the ocean? Are we going to put it into trees? What's our capacity to do that? You can see that. And these carbon reservoirs in the earth, these are copied out of this book, are huge. And some of it people don't quite understand. So there are temperature and CO2 responses that we don't quite understand, that we suspect the ocean is taking up more than our models indicate it should, that we're fortunate there, but if you don't understand why it's going there, you don't quite understand when it's going to come back out either. So there are some worries about all of this, but you can get an order of magnitude of how much is this carbon exchange going on? What are the magnitudes here? If you wanted to approach something, the numbers exist, so you can see what's the order of magnitude on what you want to do. And there are, human beings are a creative bunch. We really are. And there are a lot of proposals that you can find things. This was from Technology Review. This is from the New York Times. You can just see an astonishing array of things people are proposing. And some of them look like they'd work, and some of them look like they would have enormous side consequences. Few of them address the acidification of the ocean, which is a huge other problem with all of this. Some of them amuse me. This was orbiting trillions of teeny sunshades up in the upper atmosphere, and oh my goodness, the carbon impact of launching all of these, how would you ever bring them out, get them back down, and when you decided this was a bad idea because you killed the crop yield area of, vast parts of the planet, is one potential, it seems to me. I'm not an expert on this one, but this one strikes me as a good example to always be sure to include. But you understand, right? It's like, okay, if we're getting too hot, we'll put up an umbrella, basically, and we'll make it better. Okay, I appreciate simple thinking, I really do. I try to engage in it whenever possible because the really great ideas come from that, actually, like that solar light bulb, right, that we saw earlier in the quarter. And yet, geoengineering involves really complex issues, and that was a good example of it because there could be unintended consequences. What about crop yields? What about political destabilization? Because my country's better off than yours because of that. I think we'd better go to war over it. There's some really bad things that could happen. And if it's irreversible, heavens, if what you're doing is irreversible or not easily reversible, remember that example Terry Root had in that snippet we showed of introducing one new population to take care of the last one, and then, whoops, there was an unintended consequence. Let's introduce another one. This is all so complex. And are we going to get it right the first time? I wouldn't guarantee that. And the estimates of how it's going to work depend on lots of assumptions and on climate models, which, as I understand it, the granularity with which you can run the climate models is not great enough to really get all the information out that people wish to get. And the governance, heavens, some of you asked, such an excellent question. Some of you were asking, who decides? If you're doing a geoengineering thing, who decides where that goes? Shouldn't there be a policy? Oh yeah, there should. And what's the public acceptance beyond that? Okay, in principle, golly, I've seen towns around here go nuts over should there be affordable housing, which is still, over $1 million, but should there be affordable housing? Of course there should, but maybe not in my backyard is what people, would you think perhaps you'd get the same kind of reaction about any geoengineering techniques as well? Great, but not here. So there's a lot of human nature in all of this. And there are a range of strategies people talk about. Here's a Ken Caldera slide, and one that he has been talking about for a number of years as really looking promising because it's inexpensive, because you can deploy it rapidly, is this whole concept of stratospheric dust. Sulfate aerosol injections in the troposphere is one technique that a lot of people have gotten behind really wanting to do. About a dozen academics that I know of are really seriously looking at that, saying, it's like a volcano. If you've got a volcanic eruption and you've got a big emission of ash and SO2 and such, you will lower your temperature. So that's good. So that's what we want to do, right? Well, Mount Pinatubo, 1991, they could see the results of this. It really did work. And there's a lot of options to get aerosols in the stratosphere. And I have been in a meeting earlier this year where a couple different airplane companies were in this meeting talking about how it would cost about $1 billion. You could do it with this kind of aircraft or this kind of aircraft, but you could do it. But my gosh, do we understand that well enough? Do we really want to put that out there? Do we know what the prevailing winds will be? Who will be most affected? What will happen to rainfall patterns? So big concern, and it's got people convening policy meetings and such about what shall we do about this. So, and that iron flinger is what I call him, the fellow who wants to seed phytoplankton growth in the ocean by putting iron in, has just started doing things without any real permission. He got permission from a local fishing village to dump a couple tons of iron, and he got paid for it, with the thought that these guys would get paid back by carbon credits eventually. The last workshop I went to on soft geoengineering a few weeks ago in Washington, people were talking about that because he had done this just before that workshop. And I hadn't realized that he had promised them money from carbon credits, and that will never happen. What was their motivation on paying him for this? To bring back their fish population so that they could go ahead and keep on making their living fishing. Interesting stuff is being contemplated, and the policy, whoever was asking about the policy, and I'm sure a lot of you were thinking about it too, it's key, and it's got to be intelligent. Because on the other hand, you might need some kinds of geoengineering, and you might not want to stop all small-scale experiments from being able to go ahead because our backs may be against the wall. And so here is another Ken Caldera slide. Reflection of sunlight can offset most climate change in most places most of the time. Well, when I read this, I think he's thinking about temperature. He is not thinking about ocean acidification, but he's thinking about temperature, and temperature is really important. And he has some slides that he knows how disturbing these concepts are. His whole point is do the research now so we don't do something stupid later. But this is really striking. The idea of this is, what if you have surface air temperature rising, this is a model, and what if you turn on, and in this case turning on geoengineering, I'm pretty sure he means the stratospheric sulfate aerosol injections, you can cool things pretty quick. That's the appeal. That's why people really keep looking at this option, because no matter how bad it gets, you might be able to cool it quickly. But here is one of the really vicious things about it, and that is that when you turn it back off, let's say you decided there was some horrible consequence and you wanted to give the Earth's atmosphere a few years to clean this back out and go back the way it was because, heavens, this unintended consequence is just killing us. The problem is that the temperature rise is quicker once you turn it off, going back to the original curve pretty much, or approximating the original curve more quickly than it would have in the first place, which, as we learned from Terry Root, leads to even more species extinction. Rapid changes all in one direction are one of the key things that drive species extinction. No time to adapt. So once you're in to this kind of let's make a modification, you're in. There will be consequences to stopping. So that's a grave thing to consider as well. So here we are looking at these three that we just talked about: the mitigation, the adaptation, got to do it, the geoengineering rationale of why we do it. And then here comes what I've been working on for a few years, which has now been called soft geoengineering. Steve Schneider, when I first showed him, and Terry Root about this, dubbed it eco-engineering. The whole point of this is, and it's motivated in fair part by thinking about some of these irreversible things people think about, is you really would like to have something that was reversible or removable in case you mess up, in case there's an unintended consequence, because heaven knows, most of the time there is. And to have it be local and small so that you're having a local ecological impact. You want to minimize what you're doing. You want to try to rebuild a natural process as much as you can, rather than try to provoke some, often some different world, to try to keep things stabilized in kind of the way that we're used to, in the way that we evolved with, in the way the life on this earth evolved. And so the idea here is just, how do you do that in a way that's environmentally respectful, it's not going to have much impact. So think about the backpackers' philosophy of leave no trace, or the doctor's philosophy of first do no harm, and that's really what I'm trying to do. And so I started this in 2006. To date, it's all been volunteer, and that's partly because of the realities of funding, and partly because if your only economic outcome from doing something is that it's taking your time away from your kids and your paying job, it may keep you away from a conflict of interest of saying, I got to do this because I'm going to get rich from it. It may. But it also means things go slowly. And so I've got to say the slowly part is beginning to drive me nuts, because things have gone so much more quickly recently. That positive feedback loop of ice melting has accelerated so much that, oh gosh, is it too late to do anything? And so these recent reports, this Chasing Ice movie, it's like, God, things are pretty dire. So here we are. So how are we doing this? We've covered a lot of this. Basically, what we're trying to do is relatively inexpensive and local. First, do no harm. I've shown you this ice chart before, I think. This is just through 2007, but the ice melt in 2012 was far worse. And this is all way off the curve of what the Ipcc projections were. These were all the Ipcc projections of here's the range of what we think might happen. If you can't read these, this is from 1960 here to 2080 here. We're about here. This was the 2007 ice melt. And the red is kind of the average of all of those projections. And on 2007, we fell off the cliff. But if you look at it carefully, you will see actually this change in slope. And this is what Don Perovich, a longtime ice expert, decades of expertise, got to counsel me about a few years ago when I went to visit him in his lab. We get to speak again actually tomorrow at the AGU meeting, and it'll be good to catch up. Of just, there's no surprise. If you've been studying ice for decades, you've watched this happening. But to this degree, wow. And so dramatic ice melt blows away previous record, just wow. So they're talking about, when I first got into this, 50,000 square kilometers per year, summer to summer ice melt was kind of the typical thing in the Peter Wadham's book, which I also recommend if you decide to share my obsession with ice. Ice in the Ocean, Peter Wadham's phenomenal book. That was the number that was kind of typical of the decade leading up to 2000. But now they're talking about 1 million? 1 million were the numbers banding about recently from this last year's ice melt, from this year's ice melt. So 20 times as bad. It's just phenomenal. And it has dramatic impacts all over climate because the Arctic Ocean is 4% of the world's ocean area. It's changing the oceanic currents, sea level rise, rainfall patterns, species and habitat disruption. And why is this happening? This is something called the ice albedo feedback effect. Climate scientists have been saying that this is about 20%. This contributes about 20% to the global rate of warming. I'm suspecting with it having accelerated so much lately that it may be far worse. But the mechanism is simply that the more ice you're melting, the more open ocean area you have. And remember, ice will reflect. You know, it's just as simple as albedo, as reflecting, right? Ice will reflect about multi-year ice, old ice with a lot of air in it, will reflect back about 90%, rough numbers, of the sunlight coming into it. But open ocean, like this black desk here or this black cover here, will absorb more like 90%. So there's a huge difference in how much energy is getting absorbed. And that's what drives this mechanism of this ever-shrinking little piece of ice in the middle. So, drastic stuff. So what am I thinking about? I'm thinking about just using floating, removable, or being able to reverse the effect materials to change the albedo, but to allow evaporation. People talk about, you know, there's a lot of people whose reflex, and you might have seen it on the geoengineering sort of survey slide there of some of the photos of things people are thinking about. If you just coat things with plastic, that's easy. We know how to coat stuff with plastic. it doesn't work so well because you're suppressing evaporation. You're basically, if you think about your pool cover, you're basically remaking your pool cover, although maybe a light color instead of a dark cover. So you don't want to do that. So one of the things I've wanted to be sure to do is to allow evaporation, allow evaporative cooling in anything that we do. And you want to be able to reverse this if you're overcompensating or if your predictions are incomplete. One thing that might be the particularly sweet spot to do this is to try to protect glaciers. Glaciers have a mechanism where the ice and snow on top start melting and they start forming these melt pools. And these melt pools, these lakes, can become so big and so heavy that the pressure from them helps to tunnel through, and through a crack below. You can actually form and widen cracks, and that lubricates the slide of great chunks of the ice sheet off into the ocean. Now you've raised your sea levels again. And here's a recent picture. This is one of, I think this is from somebody from University of Manchester, but you've got similar photos from that chasing ice film as well. And it's just dramatic. When the meltwater starts flowing off, it's dramatic what's going on. You could also think about trying to make some artificial ice caps thick enough. You don't want to do this from a cost standpoint if you're going to cover a fair chunk of the ocean or nearshore area. But if you wanted in selected areas for where the polar bears are still left for breeding habitat, you could make some areas that are thicker and just basically thicker artificial ice to allow them some wildlife pullouts. And these are very rough estimates, you know. A cent per square meter, one of the raw materials I really love for this sort of thing. And, you know, maybe a few $1,000s for a polar bear pullout, just for the materials, to actually get things placed, to get them there, to get them contained in a way that you'd be able to undo it, will add cost, no doubt. And what does that mean? That means that lovely energy balance diagram that I like so much, we're trying to modify things in a few different ways. We're trying to modify the reflectivity, trying not to mess up this whole latent heat cycle, and we're trying not to mess up anything here, you know, allow cooling back radiation overnight as well. And as an engineer, I love the idea that if we think of CO2 or temperature as being uncontrolled here, and if we think about maybe darkening the Earth with one of these, you know, global SRM techniques where we might overcorrect and drive ourselves to the next ice age, that maybe if we're doing something that we can modulate, you know, maybe if we decide it's too much trouble to pull these artificial ice caps off, but golly, we're good at soot, you know, we could scatter some soot to undo the effects. Maybe we can finally modulate things so that they're just right, whatever that is. I would say whatever that is to preserve the maximum number of species that we can at this point. To just be able to move things back and forth. And whatever we do, some of you were concerned about ecological considerations. Believe me, this haunts me too, and I'm still looking for a good marine biologist to collaborate with to be sure that we pick the right kind of material and right size range so that this will work. You know, not have things, not mess up whales as they're spouting when they surface, not mess up the base of our food chain, all the algae. There's a lot of life up there in the Arctic. That under ice ecology is important. My thought is that and you want something that's not going to be an energy hog to make, so that you're spewing more CO2 and making it than you're compensating for. But the idea is if you can lever things with a small amount of material, almost like a catalyst, and regrow the natural process, you can have less impact by allowing more ice to stay than you are having from all that ice disappearing. So that's the thought. And I have played with a number of materials over time. This is my 4th or 5th year of field testing going on now. Small field tests, lakes. Once we went up to a lake in Canada where there was one of the world's good ice researchers there willing to collaborate. Mostly we keep going to the same lake up in the Sierra Nevada mountains where we're getting a lot of cooperation from their water district. And the evolution went from hollow glass spheres. Think of those 3M hollow glass spheres used in a lot of paints and building materials and such, but they tend to be very small, so small that they terrify an asthmatic like me of, do do we have a respirable problem from the fines end, from the very fine particulate? Okay, well then we got to contain it. Well, by the time you've sewn things into very fine mesh bags, like a muslin or even better, then you're going, that's going to cost a lot and be very hard to deploy. Went over to sheet form materials to get large enough areas that we could look at how much was maintained. 70 centimeter differences of ice and snow preserved under these materials when the melt came on this lake 2 winters ago, which was great. But boy, chasing sheets around, any of you who have sailed know this far better than I knew going into this, chasing sheets around on a lake with 100-mile-an-hour winds, which is a nice, I think of it as Arctic.local. It's a nice audition for what you were really trying to do way farther out. Miserably difficult, not the right thing to do. Tried some biodegradable modular materials, not very content with those, so I'm back to low-cost floating glass in mesh bags, and I wanted to just pass around to you a little sample of what I'm talking about. So humor me. It's always nice to make things a little bit real. This is a form of glass that's made out of recycled glass. It's pretty inexpensive. It's the stuff that leads to that 1 cent per square meter estimate. And I've left myself many barriers. And I'll start another one on that end. And we'll hope the glasses don't break. These seem to have a tendency to try to crack. And if that's so, bring them up quick before they leak all over your stuff. What I like about this stuff is you can get it in various grain sizes, and it's pretty inexpensive. And you can imagine containing it in things which you can get anywhere. I left the house this morning before another meeting, having forgotten to bring my little sample material with me. Oh, this must be driving the soundtrack nuts. But you can imagine containing them in fundamentally the kind of material you've got in a mesh laundry bag. And so you can pass that around too. And that's basically what we've got, although a little higher tech on our lake right now. I found an ex-military diver who makes very bags like that out of stronger materials with really strong Velcro closures. And that's what's sitting there right now. So simple. So this was the deployment. Of course, we keep on evolving our instrumentation package while we do this, and we're doing it with all volunteers. So it's people who, okay, I'm in between all my business trips. I can spend a little time with you, Leslie, to try to get some time pictures here, things like that. But interesting work. Here's this year's deployment that we just put out, trying to catch the freeze this time. We want to see how these materials act as the lake freezes. And people who worry about rogue billionaires, those are some of the words at some of these workshops, trying to deploy a stratospheric sulfate aerosol deployment, because it's within their, or some other technique, like flinging the iron. Because they could, and who could stop them, and it would be sneaky. I've got to say, something like what we're doing, the entire neighborhood stops by while we're out there, and they come and they ask what's going on, and they stare at our little platform out on the lake. It is anything but secret. And that's what it's looking like right now. It's sitting there peacefully on the lake right now. It's got a couple different kinds of mesh bags and a couple different sizes of these materials in it. And part of why I was in Washington recently was to say, for things like this that are low impact, that we clean up our mess, we go back to the same lake year after year. We put our toys away when we're done, basically. Really could have a different kind of regulation than some of these other things that are more irreversible that that people are talking about. And so that's part of the question. And we've got our instrumentation guys really work hard. We've got cameras. This is our best platform yet. We're hoping for some really good data to come out of this. Cameras, pyranometer, you want to look at sunlight coming in, reflection back, mass balance as far as you can get it for how much is it changing, what's your effective albedo, how much is it changing, how quickly snow and ice go away and such. And we found just floating these before the instrumentation platform was quite finished, floating some of these bags right at the shore, we found that with the small snowfall and ice freezing that had happened already, and then it went through another melt cycle, think of it as being like a geneticist working with fruit flies, there's a certain area up in the Sierras, certain area of time, where you can go through a few cycles. We were finding that we were retaining more snow and ice on top and underneath these materials than on open water, where you can imagine if snow's falling in, it's just melting right away if it's not below freezing yet. So very interesting. A big win would be to build back ice that doesn't melt as quickly. In the Arctic, when you are refreezing after a big melt, you tend to make thin first-year ice that has a very low albedo. It hasn't had a chance yet to build back all of those imperfections that allow it to be so reflective. It starts out as kind of that glare ice. So we're trying to look at this and see, can we build back multi-year ice to start with? And the rough cost magnitude, here's what things look like as they're melting these days, and here's our materials as they're out there. The idea is that we've got a higher albedo, and depending what size spheres, I'm actually passing around spheres that are larger even than this because they're working with my laundry bags. These are the kinds of coverage costs you get from just that material, not from putting it in a bag, not from getting it there and deploying it. So it will certainly be higher cost than that, but not ferociously awful. If we could get away with the smallest and cheapest thing and no containment, and I don't know that that's a good idea. How do you undeploy it then? But if we decided that was net benefit ecologically, $500 million per year if you wanted to rebuild one of those historic old ice melts, 50,000 square kilometers a year, which is dauntingly big. We could afford that if we decided we wanted to. And so that's what I'm trying to establish. You've been curious about what I'm doing. That's one thing. But it's important beyond the work that I can do myself there and my volunteer team. And let me acknowledge a recent volunteer who was added to the team, Susan. I mean, this is just, it's amazing how a team can grow along with you on this sort of thing. But beyond anything that we can do, and Janie's been helping, the way this thing grows is gratifying. You are not alone, that's for sure. But beyond that, getting the word out and getting other people to think about what they can do is so key. So I look at this class as one of the things that I'm trying to do for climate, and I'm really hoping you guys got some information out of it that will be helpful to you. I'm finally saying yes. When people are asking me to participate in national policy debate, I don't look at myself as that kind of a person. But you know what? If you're being asked and it's important, you say yes. So I'm going to go in February to a panel on sea ice management at Columbia. I just a few weeks ago was at this Wilson Center for International Scholars workshop on soft geoengineering. That is, should we regulate it differently than some of these other methods? I got to attend this one back in April that I mentioned to you, where the aircraft companies are telling you how inexpensive it would be to get stratospheric sulfate aerosols up there in a reasonable amount. So just all kinds of interesting ways to get the word out. And this is, I'm presenting this as kind of a role model. If you want to do something, I think these are some of the things you want to consider. What's the work you yourself can do, and how can you amplify it? And then I'm giving the first scientific talk that I'm getting to give. I've given some general interest talks on this at the AGU meeting on Friday, so that'll be wonderful. These 20 or 30,000 climate scientists up there, although I have no illusions how big my audience will be since it's early in the morning after the big conference banquet. So, but whatever 2 or 3 people are in there to talk to me, this will be great. And we've got a journal article in progress. So once you do some work, try to get the word out too. And try to get it out so that people can give you feedback about, have you considered this hazard? Have you considered that peril? Have you considered this experimental site? It all matters. If you want to hear, although you will not hear, I don't think, more information than you've heard today, but if you want to come and say hi and listen again, I'm going to be giving a talk locally just to a general audience for people 12 and up. And this is part of our attempt to raise funds for this, so that, that helps, because certainly the instrumentation and stuff takes some money. So having gone through Ice911, having gone through kind of geoengineering and kind of the class, I want to return to the class. And then I think I'm talking fast enough, we're going to be able to have time for some questions if you've got them, which is good. So this is a recycled slide from the first lecture. I think I would like to leave you with the thought of what can you do with climate challenges? You know, move past, drink in how bad it is, certainly. Spend some time feeling just paralyzed with, this is really bad. We've got a huge problem to solve. But get past that, and then what can you do about it? And so I loved what John Kumi wrote, those quotes that we started with, right? Our choices for response are mitigation, adaptation, and suffering. Okay, so let's try to work on the first two. The problem's big, it's urgent, it's misunderstood. New ventures, if you've got something great, the world needs it, you know. You've got opportunity. You may have a big idea, you're wondering, should I bother? You might think about it. You might go contact Rex Northern, go enter it at the Clean Tech Open. You know, there's a lot of ways to get things out. And it takes a lot of us doing a lot of things, I think. This is a huge problem. It is truly a planetary problem. Business needs environmentalists, and environmentalists need business. Yeah, it's true. And so I wanted to end with, if you remember that video we showed at the very beginning, that YouTube video. If you don't remember it, you can get the link from the slide set from the first lecture. You can keep it simple and have a huge impact, right? What could be simpler than a plastic bottle filled with water and a teeny bit of bleach through a hole in somebody's roof to bring light inside during the daytime? It can be simple to be wonderful. And so think about what more you need to learn and what you will try. The resources are all around. And again, just my parting shot. Yep, that is the parting shot. I hope this has helped you get a start on all this, and I'd love to hear what your adventures are, your climate-related adventures are over time. Okay, thanks a lot. And questions. You must have more questions even than you said. Oh, thank you. Thank you very much. What else? Anybody? Yes.
You were saying that the Arctic contributes about 20% to the climate.
That's what the old models were saying, and yeah.
So you're addressing a 20% problem, basically. So in the worst case, things go south, then we have to use this solution.
It doesn't solve it all.
We're going to need some more, right?
Absolutely. That's one thing that actually kind of comforted me starting it. You know, that whole moral repugnance thing was, if people got wind of this and if it were working, would they use it as an excuse to open up more coal mines? It's like, not if they're listening, you know, because it won't solve the whole thing. But 20% is a pretty good chunk to take on.
I guess the follow-up on that would be, could this be extended to use in the open ocean, or
at equatorial latitudes, for instance,
or temperate latitudes, just for the albedo effect
Possibly.
in general, without worrying about ice formation and stuff.
Possibly, and in fact, there are other methods people are looking at for brightening water too. Did I give you guys that paper? I gave you the soft geoengineering paper, which would lead you to it. There's another technique being worked on where Russell Seitz is injecting bubbles into water. He calls it bright water. And that's a really interesting thing. I look at it as kind of two sides of the same coin. You know, you can use energy to be squirting bubbles into something, and then when you stop adding energy, it stops. And so you know you've got a reversible effect right there. But you have to keep adding energy. Or you can put a material which, you know, you've done your best to make it a benign material and just let it stay out there and not have to add any energy. You know, but you could do the same thing with both. You could cool water that way. And in fact, yeah, this works well for cooling water. I've tested it. That was one of the sets of starting tests I did. So yes, it's worth doing. It's, you know, cool roofs is another, how many sides of my coin can I have here? But another side of the coin that people talked about, of just painting as many roofs or having your pavements being white to also reduce the urban heat island effect, they call it, to help to brighten things and cool things off. And that has a big effect. Can you do it then with bodies of water? And will you be not harming anything? By brightening it, you are going to reduce how much sunlight is coming down. In the Arctic, I like the idea of rebuilding ice itself because I'm trying to bootstrap a process that has been that way for a long time. You know, these glaciers that are melting now are 300,000 years old is what Chasing Ice is saying. So that's a big change. And so I'm trying to put it back, you know, so that everything that's evolved for that gets to see what it's used to again. But if you're now brightening water in areas where it hasn't been bright before, you're going to have some other untoward effect eventually. Maybe. You know, who gets to decide this stuff of what's the worst effect? Getting things warmer or having this slight darkening underneath your water column? I sure hope it's not me. You know, my vision all along and what people are hoping for is that it will be international government bodies or NGOs that, you know, or the UN who's making these decisions. It's not just lone researchers deciding, well, because we have to. Here, let's fling this, you know, like that iron guy. Does that help answer it enough? So, yeah, it should be considered. Did you have one?
Well, on that note, is there a governing body right now that sort of is taking that role? Is it just the Ipcc or the UN or?
Yeah, they look into it. You know, until so recently, when things got so dramatically different on ice melt in particular, because it's something that, you know, people were finding it hard to ignore. People really shunned the whole idea. They didn't want to think about it. There is the Royal Society came out with UK came out with a report starting to look at what geoengineering governance would be. I don't think the U.S. is doing much about it, except there's these couple workshops this year that I got to go to. So, you know, the conversation is starting, but it has yet to happen. And the Arctic-facing nations, I'm thinking, are the people that I would be talking to most, but we haven't been there yet. It's hard to find a route there because, in part, there is growing. You know, it really hasn't been there. Yeah. It's on the edge. Anybody else? Yes?
This is a down in the weeds kind of question, I guess, on thermal transfer. In your experimentation, you've laid these on open water too, not just on. Does the area under your blankets freeze as quickly as the water next to them?
Can't tell yet.
Because I would expect these things to be insulating, and I know you're allowing for evaporative.
Well, and you're also allowing, if you look at the samples making their way around, these things are very porous, and so they are getting saturated quickly too. So while there will be some thermal insulation from the material itself, you've got a continuous column actually of water coming through. I think what's making them float are the isolated air pockets in there. So it will have some, but it won't be as much as if you had a continuous sheet, I think, because you've got a lot of water there. But we don't have the granularity, so to speak, to resolve that yet. We need more tests. And
you really want freezing to happen.
You want
right?
freezing,
and
yes, you do.
And bouncing the incoming radiation back out at least keeps from heating. But if it's already warm water and you're insulating it, then that would tend to inhibit, I would think, the freezing effect. Well,
we'll get to see. Certainly in the initial freeze that we saw with, you know, just a couple weeks worth, I wish I had that photo with me. What we were seeing was that the ice was preferentially growing to some extent on the sheets over what was around it, which was really gratifying. What we could see from the top.
On top of the sheet?
Yeah, what we could see on top. One of the initial things that I thought about with this was that if you had a raft of something out on open ocean and you were snowing, that you were going to be retaining snow on the raft and maybe bridging, if you had particles, bridging them together to make a new platform. Where on open ocean it could be snowing in there and be melting into it, right? You've got a little bit of help there. But the Arctic doesn't have a lot of precipitation historically, so it's, well, that better not be the main thing you're counting on. But it does seem to work. I'm also happy to take any questions on career paths and how on earth you network into climate too, because that seemed to be the tenor of a lot of the questions people were submitting online. But maybe I covered that enough too. You first, then you. Yeah.
I got two questions. One is, how healthy is it to be spreading a lot of sulfate into the atmosphere, and the second question is, if the main issue is the amount of CO2 in the atmosphere, why not just work on carbon dioxide reducing methods like, I don't know, planting trees or algae farms or something of that nature?
Okay, two very good questions. The sulfate, I have to say I have an emotional reaction of my own to, because I carry around an inhaler for asthma. I know sulfates are bad. The people who like, so that's a gut reaction I will never get past. But the people who like that as an idea will point out that the amount that they want to put in the atmosphere, in the troposphere, first it's the troposphere, so it's far away from us, far away from where we're breathing, until it comes down in precipitation, they're saying. So I'm hearing sulfuric acid probably eventually. Got other issues with. But they talk about also, besides that it's far away from our lungs when you're shooting it up there, that it's at far lower levels than we had historically for pollution. So in my youth, in the 70s, for instance, we had far more sulfate pollution in the air than we have now. And people have actually found that as we are surmising that as we cleaned up a lot of that industrial pollution, it actually probably spiked our warming a little bit because we got rid of that anti-greenhouse gas. So the people who want to do this stratospheric injection are saying the levels we're putting up there are lower than what we used to have as pollution, and it's far away from us breathing. So that's their thought. And the second question you asked was?
If carbon dioxide's the main issue, right, then why not just work on reducing carbon dioxide?
Right. So people do, but it's not everything that people are doing. The CO2 levels are increasing far more than anything they've managed to do so far. These carbon sequestration techniques and carbon scrubbing and carbon removal techniques are really important too. It just doesn't seem to be enough yet. Look into the GSEP things, because they've done a substantial amount of things on carbon sequestration, and it's right here on campus. You can get to it pretty easily. But yes, absolutely, people need to work on that. And it's part of why I find guys like the electric catalysis people really interesting. So Will Chue and Thomas Jaramillo, because they are taking, in a really interestingly energetic way, right? You could maybe do this with photovoltaic, well, not quite photovoltaics, but solar powered, to allow you to convert CO2 into useful other things. It's really pretty neat. And sort of avoid the problem that way too. The problem people have with scrubbing CO2, of course, is the concentrations are teeny. And in fact, you know about what the concentrations are. What are we at right now? 350? No, we're over that, aren't we? 350 ppm? 390 ppm now. So that's a pretty small amount to try to scrub. So then people who are trying to scrub at the stacks of, say, coal plants, well, that's more rewarding, right? You've got a higher concentration there, but still, it's a pretty diffuse and pretty difficult transport problem. So are you going to spend more energy and thus generate more CO2 than you gained? But it's key. If you've got the right technology, it's really key. The world will beat a path to your door.
I was looking at more
trees, yeah.
Yeah, I mean, just
yeah, they matter. And to stop deforestation matters a lot. Yeah, so I agree. It doesn't seem to be enough somehow.
I did a lot of work with algae.
Oh, good.
And one thing that I thought a lot about, and you have to keep in mind, is when you're talking about trees, and deforestation is, I mean, stopping that is really important, but when you're talking about trees and algae, the carbon cycle is so short that, I mean, you're taking carbon in, you're sinking it, but then the trees and the algae die, and they, so it's not like a permanent sink, whereas the fossil fuels that we're burning, that's really, really, really old carbon. So just saying, oh, well, we'll get some plants and things to sink this carbon into, well, they're going to die and decompose. so you really need to think about the scale of the carbon cycle you're looking at. So we decided it wasn't super worthwhile what we were looking at.
Important and sobering. Yeah. What's the average age, do you know? You sound like you might, of the fossil deposits that we're using. Are we using 100,000 years worth of stuff?
Millions of years.
Yeah, that's hard to make up for in a year of tree planting, huh?
Well, I was looking at algae and they die pretty quickly, so.
Yeah, I read somewhere that on tree growth and carbon sequestration, it was, I think a forest of about 100 years or newer was still sort of net positive in sequestering carbon. But after about 100 years or so, then it's sort of an unusual balance of new growth versus decaying. And that particular article was suggesting that we should chop down trees and sink them to the bottom of the ocean. But that's another one of those like terrible ideas that, you know.
Anaerobic digestion and release methane instead.
Yeah, it's not a
Methane.
viable idea.
I didn't even talk about permafrost, but of course as the ice melts, people are becoming so alarmed because methane plumes are appearing in the ocean. And methane is a far worse greenhouse gas than CO2. So that's the other sort of unpredictable amount that's poised to hit us as well. And it's another huge concern to try to stop or slow down ice melt if you can. You've had a burning question for a while, sir.
I was just wondering if you've had a chance to look at how long your glass beads will last in a freeze-thaw cycle.
Not yet.
Not yet, okay.
And if they went away after a year, but were still incorporated in the ice to some extent, that would probably still be
Sure, that'd be fine, yeah.
One of the things I worry about is, and I've seen this over time now, having had a bunch of them just out in a wading pool over a long time, and water coming in from rain and then evaporating, and kids and cats attacking it and stuff, that some of them are sinking after a while. And so, but it's the order of many months, but it's these may not be around floating for so long. Is that a problem? Maybe that's good. You're basically making your floating sand into more like sand, sinking to the bottom. But again, the life cycle questions, the effects of any, well, what if you had a light dusting of this on your seafloor? Is that going to be an issue for something living down there? All this stuff has to be looked at. And the collaboration, I'm serious. If you folks know any good marine biologists who want to collaborate, that's a word I will keep putting out because we don't have one yet and we need it. Anything else? Okay. It has been, and we're at 2:03, so the timing is terrific. It has been such a pleasure getting to know you folks. Thank you so much. Your summaries, your questions, reading those have just made my week time after time. And thank you. I wish you all great luck. So let me say to you, thank you.